Good evening again. It barely seems like 5 minutes since I was last talking to you, and this is Ancient Light. You can see from the subtitle, it's about imaging a quasar without using a telescope. You may have noticed that things have been different for the last 12, 15 months or so. In 2020, life as we knew it changed because of life in lockdown. This object gave rise to a lot of these objects scattered over floors and pavements all over the place. People tended to look down, but I remembered Stephen Hawking's words. Remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. I thought, right, okay, remember to look up at the stars. How far up can you actually look using a camera but not using a telescope? That's when I decided that in the middle of last year I needed a challenge, and this was the challenge I set myself. We all know that the universe is vast and ancient, and we know that large telescopes, like the Hubble Space Telescope for instance, have imaged galaxies that are billions of light years distant. Is it possible to capture an image of one of these very remote objects but without using a telescope? And the spoiler alert is, because I'm giving you this talk, yes, it is. So I read this paper about luminous quasars. We won't bother about all the detail, but we have to think about what a quasar is. A quasar is the nucleus of a galaxy. It's a particular type of galaxy with a nucleus that's called an active galactic nucleus. It's the nucleus of a galaxy that emits enough light to be seen at enormous distances, for instance, distances of many billions of light years. So a quasar is an ideal object if you want to see as far as possible. That's an artist's impression. We don't actually know what a quasar looks like because we've never seen one close up. But it is thought that what's going on in the heart of a quasar is that there is a supermassive black hole, similar to what's in the centre of most galaxies, but in a quasar that supermassive black hole is feeding on surrounding matter which is falling into the black hole, and on the way in some of that matter is converted to energy and it produces a huge amount of radiation. So a very distant object has had its spectrum measured by this particular group of people in this paper that was published in 2019. They took the spectrum of a particular object that I was interested in because it looked very distant and it was high in the sky as seen from the UK. That spectrum, looking at the intensity of light from the quasar as a function of the wavelength from blue on the left to red on the right, that doesn't look like a very interesting spectrum. But the interesting feature that came out of this when they looked at this was that that feature there, which appears in the spectrum at 6,500 angstroms, these are units of angstroms. If you prefer, divide by 10 to get units of nanometers, so 650 nanometers. That particular peak was identified as the same peak that would appear in the ultraviolet part of the spectrum if the object wasn't moving. So remember, when objects are moving away from us, the spectrum gets redshifted, in other words, shifted to the right. So a particular peak that should occur at 1200 angstroms in the ultraviolet part of the spectrum has been shifted all the way to 6,500 angstroms by the recession velocity of this object. It's moving away from us so fast, it's gone from 1200 to 6,500. And to quantify the redshift, we take how much it's moved by. In this case, 65 minus 12 is 5,300. We take that number and divide it by the original wave number, in other words, 1200. The difference of these two numbers, 5,300, divided by 1200, that quantifies the redshift. And the redshift comes out to be 4.3 for this particular object. And a redshift of 4.3 means that this quasar is very remote. And we'll talk about the actual distances in just a few slides' time. So I decided, right, I'm going to get out my camera and I'm going to get out my telephoto lens. the particular beastie I've got here, the Nikon camera, and a 300mm lens. Not a particularly massive lens. 300mm is quite modest by today's standards. And I mounted the camera and lens on a sky tracker, a star tracker. That white box on the left-hand side is basically just a motorized box that will turn the camera at 1 revolution per day. So as long as you use this little polar scope here to point and line up on Polaris, then this axis should be lined up with the Earth's axis, and therefore rotating the camera at once a day, the camera should follow the stars if everything works correctly. Now, this particular camera and lens that I'm talking about, this is the equipment that I use for wildlife photography. This is in no way customized, in no way modified for astrophotography. It's just the particular combination that I would use if, for instance, I ever get back to going on safari in Africa, which I like to do every once in a while, in a year or two's time when it might be possible again. This is the camera and lens that I would use, for instance, to take pictures of zebra, like this particular picture here taken a couple of years ago. So if your camera equipment is designed to work in daylight and take pictures of zebras, can that same equipment capture a quasar on the other side of the observable universe? That's the question I was asking myself. So I figured out where the object was. I looked up its coordinates, and its coordinates happens to be the quasar is in the constellation of Draco. So there's Draco, there's Ursa Minor on the right hand side, there's Polaris of course, and this is where the quasar is located. That dot there is not the quasar, that happens to be a 5th magnitude star, which luckily is right next door to the quasar in terms of our line of sight, so I could see that by setting up the camera. If I knew that star was centered in my camera field of view, I knew the quasar was sort of right next door. I focused on a nearby star which was about 8th magnitude to make sure the focusing was spot on, and then took a long exposure. Not as one single long exposure, but I took a series of short exposures and added them together. A number of advantages in doing that. One advantage is your tracking doesn't have to be perfect for 2 hours. If it happens to drift ever so slightly, that's okay. You've got lots of images. You make sure they're all lined up on top of each other before you add them all together. The other advantage was that during the 2 hours of this particular night, some clouds were scudding by, so by taking a large number of short exposures, afterwards, when it was all done, I simply went through them all and threw away the ones that had clouds spoiling the image and added together all the remaining images, which added up to something of order 2 hours exposure. There's the bright star. It happens to be called 80 Draco, right in the centre there. And the quasar should be in the middle of that square according to its coordinate. So I took the image that I had taken on that particular night in July of last year, and I blew it up to see what was there. And there, as indicated by the 2 red lines, there is the quasar. So yes, you can capture this very distant object. Most of the light from the quasar, by the time I'd taken these images and lined them all up to get my 2-hour exposure, most of the light from the quasar had actually ended up in just about 1 pixel. In this little blow up on the left hand side, I've just brightened some of the fainter pixels. You can perhaps see a couple of stars in the background there as well. I've brightened some of those other pixels just to make it a little easier to see, but most of the light has gone into that single pixel right in the middle of the quasar there. Just a quick diversion, just to say what we could expect in terms of resolution. This is a telephoto lens. It's an f4 lens, so its front element is about 75mm or so in diameter. From that you can calculate what resolution can you expect if the lens is perfect, if there were no aberrations in the lens, and given that I paid quite a few £100 for this lens, I would hope that there's no serious aberrations. If it was essentially perfect, you would expect to be able to resolve to angles down to about 9 microradians, 9 millionths of a radian, which equates to something a little bit less than 2 arc seconds. And looking at the size of pixels in the chip in the camera, the pixels are a little bit larger than that. The pixels would be about 15 microradians, corresponding to about 3 arc seconds. And on that particular summer's evening, the seeing might have been of order 2 arc seconds. So the resolution of the lens, the resolution of the camera, and the seeing are all in the same sort of ballpark of about 2-ish arc seconds. Just for comparison, just to give you an idea of size, if we took an object the size of the Milky Way galaxy and placed it at many billions of light years, how large would it appear? Well, it would appear to be a couple of pixels or so. That gives you an idea of what we're looking at here. Just returning to this particular crop of this tiny region, it happens to be about 8 by 8 arc minutes, something of order 1/10 of a degree on a side. As well as identifying the quasar in the middle, I checked these blobs because some of them didn't look very circular, and I thought that the tracking was okay. So I figured some of these non-circular blobs might be galaxies. So I checked that star field against a star field from a research telescope and identified that indeed some of these objects aren't stars, some of these objects are galaxies. And there are at least 10 galaxies that I could see. Some of those might be too faint to show up on your screen at the moment, and some of them definitely look like stars, so you'll just have to take my word for it that I've identified those as being non-stellar objects. So if I've caught 10 of them in that particular crop of the image, assuming there's the similar number everywhere, and there's no reason to assume otherwise, then if I've caught 10 of them in that area, then the number of galaxies in the whole image is probably about 7,000 galaxies. So I've called this the Barrett Deep Field simply because, by coincidence, the number of galaxies I've caught in that image is probably about the same, it's in the same ballpark as the number of galaxies that were caught in the Hubble Deep Field. I'm not claiming this image is as good, but it's interesting to note that the numbers work out very similarly. So what about the distance? We've said that yes, we can catch the light from this quasar, but just how distant is this quasar? What is the distance to the quasar? Well, the distance is a bit of a problem. Light left this particular galaxy. I'm going to use galaxy and quasar interchangeably. A galaxy with a quasar at its core, effectively, produced some light, and that light left the object, the quasar, a long time ago on its way to Earth. So you could say that was the distance then, when the light left. But of course, as the light is on its way to Earth, the universe continues to expand. The galaxy was at a particular distance from us when the light left, but throughout the light's journey, the universe continued to expand and the galaxy is along for the ride, so the distance is increasing. And eventually the light makes it to Earth and enters my camera, at which point the galaxy is even further away from Earth. So when we talk about the distance to the quasar, what do we mean? Do we mean the distance as it was when the light originally left? Do we mean the distance that the galaxy is now from Earth? Or do we mean the distance that the light has travelled, which is more than the first but less than the second distance? So which of these three distances is the correct one? Well, there's no such thing as correct. They are just three ways of defining the distance. And there is yet one other problem, and that is when we think of the light travelling from the galaxy to the Earth, remember throughout its entire journey, the light is travelling through space and space is expanding at the same time. So it's actually quite tricky to work out how far has the light travelled, because the light is travelling through space and space is changing as the light is travelling through space. If we want an analogy to try and make that a little more concrete, we can think about a swimmer moving through water. If a swimmer can swim through water at 2 meters per second, but the water is flowing because space is expanding, it's like the water flowing against the swimmer, it's like swimming against the tide. The light is moving through space, but space is being stretched. Another analogy that's quite useful in terms of thinking about this is thinking about an ant moving along a rubber band. if we think about an ant moving along a rubber band, we can see how far the ant has moved. But what if we start stretching the rubber band whilst the ant is in motion? Then you can ask the question, how far has the ant walked? But it's a difficult thing to measure because every step the ant takes, the rubber band underneath his or her feet is being stretched. So it's a tricky problem to actually work out. But it can be done as long as we have some idea of how the universe is expanding. In other words, if we have some mathematical model which tells us the universe is probably expanding like this. It used to expand at that rate and now it's expanding at this rate, and this is how it's expanded all of the time between a distant time in the past and the present. And that's what these curves show. They're calculated curves for what is the distance to an object for a given redshift. In other words, if we were to look at an object which has a redshift of 1, that's a particular distance from us, and we can calculate how far the object was, the blue line, when the light left, how far the light has travelled, that's the green line, and where is that object now, that's the red line. You can see that if the object is not very far away from us, if the redshift is 0.1 for instance, then these three lines are effectively the same thing. In other words, the universe hasn't changed much from the length of time it took the light to go from the object to us, if the object is very close. But the further an object is away from us, the more the universe expands in the interval between the light leaving the object and the light arriving at us, which is why these three curves diverge away from each other. So let's have a think about what that means for our object. Rather than think about the universe in its entirety, let's just think about that galaxy at a redshift of 4.3. From our understanding of how the universe expands, we can read off the numbers corresponding to our quasar. And there are those three numbers there. Let's just get rid of those lines because they're distracting. Those are the only three numbers we care about at the moment. So what it means was the quasar was about 5 billion light years away from us when the light that we caught here was emitted from the quasar. And the light has been travelling for over 12 billion years between when it left and when it arrived in the camera. Remember, the universe is 13.8 billion years old, so 12.4 is actually about 90% of the age of the universe. The light that made that image has been travelling for 90% of the time that the universe has been in existence. That is a really mind-boggling number. And during those 12 billion years, the universe has continued to expand and the quasar is even further away. The quasar is now 25 billion light years away because the universe continued to expand during that light travel time of 12 and a bit billion years. But if you're still awake, you may notice something very interesting. The quasar has gone from 5 billion light years distant to 25 billion light years distant. It's changed its distance by 20 billion light years over a time period of 12 billion years. So a quick back of the envelope calculation tells us something very interesting. During 12 billion years, the distance to the quasar has increased by more than 12 billion light years. Speed is distance over time. It's changed by 20 billion light years in a time period of 12 billion years. That means that the object, the quasar, is moving away from us on average by 1.6 times the speed of light. In other words, it's been moving away from us at more than the speed of light. It is receding faster than the speed of light. Not only that, if we do have a reasonable understanding of how the universe has expanded, we can work out what its speed was originally and what its speed is now. And we can actually plot that, and it turns out that when the light left the quasar, back in these early days of the universe, the quasar was receding from us at approximately 2.2 times the speed of light. and it started slowing down. That's perhaps no surprise. We're in an expanding universe, and after the Big Bang produced the expansion, gravity presumably has started to slow the expansion down. So it's no surprise that the speed started to fall. But the real surprise is what's going on after about halfway. It's going up again. After initially slowing down, the quasar is now not only moving away from us, it is accelerating away from us. That line is now going up. Its recession speed is increasing day on day on day. It's moving away approximately 1.7 times the speed of light, and every day it's moving away a little bit faster. In other words, the expansion of the universe is accelerating. Something that was discovered 20 or so years ago, and it's very nice to sort of look at this particular model of how the expansion has changed and actually see that in terms of our quasar accelerating away from us. So we can't get that from the photograph, we can only get it by modelling how we think the universe has behaved. But it's interesting to note that the average is about 1.6. It started off faster and it's currently faster. It decelerated and then accelerated. And it has been accelerating for the last, 5 or 6 billion years. Remember, this doesn't violate anything that Einstein said about objects moving faster than light. The light is moving through space at the only speed it can move through space, the speed of light. The speed of light in a vacuum, c. But space itself is expanding and the galaxy is along for the ride, and so the galaxy is being carried away from us because it's being carried, if you like, by the expanding universe. So objects, including light, can only move through space no faster than the speed of light, but space can expand at any speed it likes. And it was originally expanding much, 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 much faster than light, but then it slowed down and now it appears to be speeding up again. So that was a big surprise 20 years ago because nobody expected that curve to have an uptick in it. If we think about it in terms of the light, here I've plotted on a chart of distance away from us on the horizontal scale and time since the Big Bang on this vertical scale. So there's us at zero distance, 13.8 billion years after the Big Bang. So there, the little amber dot there is us here and now. And this green dot, 5 billion light years away from us, something like 1.5 billion years after the Big Bang, remember 12 and more billion years ago, that's when the light left the quasar. If the quasar then was 5 billion light years away, you would half expect the light to get closer to us and closer to us and closer to us and closer to us, and as time went by. Remember, time goes vertically in this particular plot. So you might expect the light to get closer and closer and closer to us. But remember, the light is trying to move through space, which is expanding faster than light. This is like a swimmer swimming through water that's flowing against them, and the speed of the water flow is faster than they can swim. So they get dragged backwards by the water. It's the same idea here. So actually, because the quasar is receding from us faster than light, or space is expanding faster than light if you prefer, the actual path of the light is not that dotted arrow. The path of the light is more like this. Oops. The light starts from the quasar, it's trying to get to us, but actually it's being dragged backwards, and for the first 2 billion years or so, the light is actually getting further away from us. It's trying to come towards us, but space is dragging it backwards. And for 2 to 2.5 billion years, that is what's happening to the light. It's getting further away from us. But by the time something like 4 billion years after the Big Bang, finally the light starts to make some headway and eventually does make it to us. It takes obviously 12 billion years. Excuse me. So that is weird in itself, the idea that light is trying to get to us but is being dragged dragged backwards by the expansion of the universe. That takes some getting used to. Even when you read it, you still have to stop and think, huh? And to try and get your head round it, you need a few minutes thought. If we think about what the quasar was doing, the green line is what the light did. As soon as the light left the quasar, it was dragged backwards for a while, but eventually made it to us. What was the quasar doing? Well, the quasar, remember, is just along for the ride as the universe expands, and so the quasar goes flying off to the point where, at the now point of 13.8 billion years, it's something like 25 billion light years away from us. I've shown it as a dotted line because remember the previous slide showed that the velocity, the recession velocity of the quasar is actually changing. It was fast and then it slowed down and now it's getting fast again. So that line there, it should really be changing its gradient because the velocity isn't fixed. The velocity was high and then low and then high again. So that should be a little bit of a wavy line, but I couldn't work out exactly what the curve ought to look like, so I just put it as a dotted line to indicate that when the light and the quasar parted company, the light took the green path and the quasar took the red path on this distance time graph here. When I look at the image, it might only be a pixel, but I like to think about the journey that the light has had. The light was emitted by the quasar 1.4 billion years after the Big Bang. The light travelled for something like 8 billion years before even the Sun and the Earth existed. And the Sun and the Earth were born some 4.5 billion years ago, and the light continued its journey for those 4.5 billion years. Life evolved on Earth, the light travelled on. Dinosaurs came and went, the light travelled on. In the last million years or so of its journey, the light arrived at the edge of our Milky Way galaxy. It would have crossed a few spiral arms and then entered the solar system. In the last few hours, it would have crossed the solar system, arrived at Earth, travelled through the atmosphere in a fraction of a second. It would have hurtled towards England, dodged a couple of clouds, entered the lens, and arrived at the sensor of the camera. Just a pixel, but what a journey. Here's a graphical summary of what I've been saying. I took my camera and telephoto lens, nothing special, just an ordinary camera and telephoto lens, put it on a star tracker so that I could take a long exposure, pointed it in the direction of Draco where I expected this quasar to exist, and right next door to the star you can see at the centre of the main image, in the inset in the top right, you can see that is the quasar, confirmed by plate solving that particular image to make sure I had the coordinates absolutely bang on. So yes, without a telescope, it is possible to catch what I think of as the quasar's ancient light. Thank you all for listening.